So let's talk about the electric field from a point charge as a way to discuss analytical models. So first I'm going to start by drawing I'll draw a circle. Keep in mind that we're drawing, of course, in a two-dimensional plane, but the idea is that this is representing a sphere or a small point that represents an actual three-dimensional object. I'm going to designate this point charge with the letter Q+. Q is a common variable that we will assign to point charge, whether it's lowercase or uppercase really doesn't concern us. But the idea is that we're all familiar with the concept of charge without getting into quantum mechanical details and philosophical discussions. We've experienced electrostatic discharge walking across a carpet. We've seen lightning strike the earth. We've seen we use charging for electronics devices. We're comfortable with the idea of electrons flowing around. This is a positive charge. And one of the models that we use for this is a field model. So what we can say is, given a single point charge that has a value of Q, what the fields look like emanating from that charge are basically radial directing. So these lines are representing what's called the electric field due to this point charge. A graphical model of this will basically have the same sort of look in all directions for an electric field. And I think you get the basic idea here. So every one of these vector field lines is represented by the letter E. And the idea is that I've got a field. If I look outside of that source, I can think of permeating that entire space for infinity in a free space model, that there's this electric field force that exists everywhere, and they're all designated by this letter, this capital letter E, with a vector sign on top of it. So the arrow that we see on top of the letter indicates that it is a vector quantity. So what's the definition of the electric field? This gets a little abstract, but what we can say, what we commonly find in physics books, is a definition. If I use 3 lines to represent the definition, we can say the definition of the electric field at any point in space is defined as the force exerted from the electric field. That force is a vector quantity itself. That's where the electric field gets its vector nature. That is imposed on a small test charge. So this Q0 is small in the sense that it's not going to contribute its own electric field to the distribution that you see coming from our Q+, our source charge. So again, that gets a little abstract and philosophical, but the reality is that we have no way of measuring the electric field itself. The electric field rather is inferred from the force exerted on charged objects in the vicinity of each other. So a mathematical definition for this, or I should say a mathematical equation for this, can be determined through, in our case, it's been hundreds of years of physics experiments by people like Michael Faraday that have determined these characteristics of electric field and how they relate to charges. So what we're going to do is, instead of calculating forces on neighboring charges due to point charges, we're going to write out the equation for the electric field. So I've got a definition up top, but in this equation, I'm actually going to put some mathematical basis to it here. And the equation that we use for the electric field for a point source is going to be Q, which is the charge in question, divided by a constant. And it turns out it's a couple of constants, 4 pi epsilon naught. I'll get to that in 1 second. And I'll go ahead and represent this 1 over r squared, and I'm going to give it a direction of r hat. So what does all this mean? So let's imagine that I have an observation point that's going to be down here. And let's just make this would be equivalent to our test charge. The red circle really is supposed to represent an infinitesimal point, And what I'm saying here is that if I think of the distance from the center of this point charge to my observation point, I can represent that by the displacement r. And that's what this r squared is in the denominator. Okay? So the vector nature is coming from just the same unit vector that is defined by connecting the center of Q plus to my observation point. So one way to think of this is if I draw a little arrow here that is attached to the end of my displacement vector, this simply points the direction. So I'm going to put an r hat there. And we're not going to talk too much about the mathematics about this right now. We just want to introduce the concept. So what I can do is I can connect this letter r here to the displacement. So that's in the denominator r squared. If I move this observation point anywhere in this observation space, the displacement is going to move along with it, and so will the direction of that unit vector. So r hat is always pointing outward from the observation point to the area to the location that we want to observe and calculate the electric field.